be until Wednesday for you guys. So we started into chapter 2 last time, which then, so we've talked about like what are the subatomic particles and how do you determine using the periodic table. So I really think that this is sort of this is when you know you're going to have something like this, where you're given an element and you need to be able to tell me how many protons, neutrons, and electrons are there. So if you're given the periodic table, and you will get this, right? So you don't have to write down anything on your note card that is already on your periodic table, but you might have to write yourself a note on, remember that atomic number is numbers of protons, numbers of electrons, that the number of neutrons by subtracting the atomic mass minus atomic number. So you might have to write yourself notes about like how to remember how to do that, because you know you're going to have a couple of these. So I gave you 3 different ways that you might actually have to use information. One of them is you might have the name and the mass of the element. So like this one is iron 57. So when you see iron 57, one, you have to look up what on the periodic table. What is the symbol for iron? It is Fe. So you need to find Fe on the periodic table. So first, you need to find Fe. So iron is one of the 30 elements, names, and symbols that you need to know. So now if you find Fe, find it, it's number 26. Does everybody see it? So how many protons? Ooh, I didn't mean to do that. I never know how I do this. It just randomly happens. So I have protons, 26. That means I also have 26 electrons. Remember, P equals E, right? The number of protons is equal to the number of electrons, so I have 26 of those. So those are always going to be the same. Now, to find out the number of neutrons, what am I going to have to do? Yes. So 57, that's telling you the mass of this element of iron. So 57 minus 26 tells you that it is 31. Okay, so if you're given the name and the mass afterwards, then use that as the mass. Now, if I just asked you how many protons, neutrons, and electrons is there in sodium, then you would just use the periodic table, find the mass of sodium, round it to the nearest whole number. But if I give you the mass, then you're going to use that number. So see the difference between them. So same thing here. So this is P with a 34 above and a 15 below. I can actually write it a little bigger over here. 34 above and a 15 below. Remember, they call that symbolic notation. It's different. Notice that the atomic number, atomic mass are flipped. How many protons? 15. So protons, 15. That's the atomic number. That means how many electrons? 15. Because remember that those are the same. The atomic number, the smaller number, is always the number of protons and electrons. Now, how do I figure out the larger? I got to subtract. So that would be 19. Okay, so that symbolic notation, you should be able to figure out protons, neutrons, and electrons. Given the mass number after the element name, you should be able to figure out protons, neutrons, and electrons. And then if I just gave you an element, like sodium, then you would know to use the periodic table. So then you would find Na on the periodic table. You know then that there's 11 protons and 11 electrons. And then you would take the atomic mass, round it to the nearest whole number, subtract to figure out the average number of neutrons. Okay? And the reason that the periodic table is not have an actual number for its mass is because of the fact that there are some atoms of an element that may have different numbers of neutrons. They have to have the same number of protons, because that's atomic number is what defines the element, but some atoms can have different numbers of neutrons, which means they differ in mass. So if they differ in mass, they have a different mass number. So for example, I had carbon. Carbon can exist as carbon 12, carbon can exist as carbon 13, carbon can exist as carbon 14. They're all carbon, so I know that all of these have 6 protons and 6 electrons, because if you find carbon, C, on the periodic table, you see its atomic number is 6. So that you know there's 6 protons and 6 electrons in all of those carbon isotopes. But the number afterwards is what differs. So the first one, carbon 12, has how many neutrons? So I have 6 neutrons because I take 12 minus 6, tell me there's 6 neutrons. But carbon 13 would have 7 neutrons, and carbon 14 has 8. So they still have the same number of protons, same number of electrons in a neutral atom, but they can differ by numbers of neutrons and still be carbon. So when they went to figure out the atomic mass for the periodic table, they didn't just pick a single isotope. They based it on the abundance of the isotopes found in nature. So for this one, carbon 12, or carbon, if you look at carbon, notice that when you find it on the periodic table, 6 is above, 6 protons and 6 electrons, but then it's 12.01. So the reason it has the decimal place is because 99% of the atoms of carbon found in nature are carbon 12. So almost all the atoms are carbon 12, but there's a 1% of them that are carbon 13 and a very small percent of them that are actually carbon 14. So when they figured out and took their amount, their relative abundance compared to their mass into account, this is why the number, it's a little higher than 12.
I didn't get the carbon 14 one. I got the carbon 13. It was 7.
6, 7, and 8. 12 has 6 neutrons, 13 has 7, 14 has 8. They just differ by 1 neutron.
With no charge.
Right, remember N would be a little 0 because there's no charge to the neutron. But all of those carbons have the same number of protons and electrons. They only differ by the number of neutrons, so they differ in mass. Okay, and you can actually see it if you look at this chart right here. So that chart shows you numbers of protons, and they're the same in all of them. Numbers of neutrons, 6, 7, 8. So when you look at the periodic table, the number for the atomic mass takes into account the fact that that elements have isotopes, that there exist atoms that belong to carbon that have different numbers of neutrons. But the one that's closest is going to be the closest or the most abundant isotope type. So when I look at carbon, the mass is 12.01. When I round it, that means the most common isotope is going to be carbon 12. Just like if I look at sulfur, what would you say is the most common isotope of sulfur? It'd be sulfur what? Sulfur 32. So if you look at sulfur, it's 32.07. I just round it. So I know that there's got to be more 32 than 34 or 36 or 35. There's more because that's the closest average number. So we are not going to do any calculations, but I did want to explain why the atomic mass is really an average. That is why you have all those decimal places when you look on the periodic table. But for you, just always take the atomic mass, round it to a whole number, and we're going to call that the mass. It's really the mass of the most common isotope, typically. If it is less than 5, round down. If it is 5 or greater, round up. Just use that as the rule in rounding. So what is significant about this? So first off, I'm going to tell you that radiation chemistry, so this understanding about subatomic particles and about isotopes, really is only about 100 years old. So this came out, Henri Becquerel, so this French scientist, he was studying rocks. He was studying different elements, and he and Marie Curie, they were extracting unusual and low percentage rocks out of the earth. So the one that he had and collected was uranium. So if you find U on the periodic table, what's its atomic number? Find U. It's way down at the bottom. 92. That means there's 92 protons and 92 electrons. That is a big atom. considering, like hydrogen's 1. Carbon's only 6. This one has 92 protons and 92 electrons. But then look its atomic mass. Its atomic mass is 238. That's humongous. So that's like 146 neutrons. That's a lot of neutrons. That's a lot of subatomic particles compared to the ones that you typically find in the body. So he extracted uranium from the earth, isolated it, and had it as a sample in his lab. So he was trying to kind of characterize it. So what is the characteristics of uranium? How is it different from other metals? Well, also in his lab, he had some film. So photography film. So they would use photography film to take pictures of different kinds of things as they would isolate them. And so they could document the research that they were doing. He found that if that film was anywhere near that sample of uranium, if he developed the film would show up white. It would show up white, and white is what happens when film is exposed to light. So if you have film that's not exposed and you develop it, it'll just look black. But once it's exposed to light in different patterns, that's what develops a picture. Well, his film develops it, completely looks white. So he thought, well, maybe it's just bad film. So he gets another roll of film, another package. And this is way back when. Do you remember how the old time film? They were like big boxes, and you would have to like look through this little viewer, and they would put that big sheet over the top of them so that they could keep the light out. So film was like a plate, almost like an 8x10 plate that you would develop. So this is like super old school kind of film, not like digital cameras or anything, okay? So he got more film, had it in the lab, took photos with it, developed it, it's all white. So he said, there is something in this room that is exposing this film. So he started putting the film in different spots in the room, and he found if he put it anywhere near the uranium, it would turn white. So he said, by experimentation, he came up with this idea that there is energy that I cannot see, but there is energy coming off of this element. And that energy, it's radiating. So this is where radiation, this idea of radiation came from. It's radiating off of this sample. It's coming from the substance itself. He said it is coming from the nucleus of these atoms. So this is where nuclear energy and nuclear radiation was really first described. So it was only like 125 years ago. So this is like considered a pretty new branch of chemistry.
On my Moodle page, where can I see you reading this off it? Don't we have this in here?
Oh, you mean like the PowerPoints?
Yeah.
So if you go to Moodle and you go to the PowerPoints, this is chapter 2. So like you can just like download it and open them. So these are all there.
Yeah, I don't know which one you're on.
Chem 130, section 21, right? And if you roll down in the modules, you should find the PowerPoints.
2 more.
This is chapter 2. So if you open that module, they should all drop down and you should be able to see them. Okay, so he kind of coined this term radiation. This is this energy that's given off. And so he's defined or said, well, not all elements do this, but the big ones tend to. And so he theorized big atoms are not very stable. So to become more stable, they break down. So when things break down, they call that decay, right? So decay or decomposition is the breakdown. So radioactive decay is just the way that atoms break down to become more stable. And uranium's a good example because it's so big. Large atoms. These are talking about atoms that have atomic numbers larger than 83. So if you look on the periodic table, going up to 83, everything over 83 is not very stable. So most of those are radioactive. Most of those undergo decay. A lot of it has to do with their numbers of neutrons. So like if we look at uranium, so we said uranium is 92. And it has 238. So this has 92 protons, 92 electrons, which in itself is really big, 92 protons, 92 electrons. But if I subtract those two numbers, That is 146 neutrons. Big atoms with lots of neutrons, more neutrons than protons, they tend to be the most unstable. And I think of it as like, I think of the atom. Remember I told you that protons and neutrons are in the nucleus? And remember that nucleus is like that really small, dense core right in the center? So if you're trying to pack all those protons and neutrons, there's not much space. And so the atom would be more stable if it could just get rid of some of them. If it could bring those numbers more to a manageable level. Radioactive decay occurs to allow atoms to do this. So we are going to talk about the three most common, and we're not really talking about positron or neutron decay, but we're going to talk about alpha, beta, and gamma. These types are the most common, and in fact, if you are using a radioactive substance or if you're exposed to a radioactive substance, most commonly it's one of these types, especially in health science. Whether you're talking about nursing, dental hygiene, veterinary science. So here's the first one, okay? So alpha. Now first, when they talk about alpha, they use this little Greek symbol, which is the alpha symbol. And to me, it just looks kind of like a funny little A. Some people say it looks like a fish, especially the way that I draw it. Okay, so I'll oftentimes draw it looking like that little A, kind of like a fish without a tail. Some people say it just looks almost like an italics A. So just remember that A is referring to alpha. Okay, so you see it up in this corner. So that's the symbol for alpha decay. When alpha decay occurs, a big atom, and in this case, it's uranium, a big atom actually spits 2 protons and 2 neutrons out of its nucleus. So they come like shooting out. So when that happens, protons have a mass of 1. Neutrons have a mass of 1. So if I lose 2 protons and 2 neutrons, the mass is going to go down by how many? So if I lose 2 protons, each with a mass of 1, and 2 neutrons, each with the mass of 1, then that means the mass is going to go down by 4. So, and remember that the atomic mass, when you write it in that symbolic notation, the atomic mass is above, and it's always the bigger number. So the mass is going to decrease by 4. So instead of being 238, now my product is going to be what? 234. So it's going to go down by 4. Now the atomic number, if 2 protons get shot out of the nucleus, then the atomic number is going to go down by 2. So instead of being 92, now it is 90. But now if it's atomic number 90, it's not uranium anymore. So you have to look on the periodic table, find atomic number 90. What's its letters? It's TH, which is thorium. Remember the god of thunder. So thorium. So do you see that? So it actually changes, it like decays from one element into another. I am not going to ask you to complete the reaction, but if you see this reaction, I want you to be able to tell me that it is alpha decay. So in this, the symbol changes as well. So one way that you can pick this out is you will always see this. The helium with the 4 and the 2, it's a helium nucleus, that will always be a product. And it really should have a positive 2. It's always a product. So that's really all you have to look for with alpha decay. If it shows you a reaction and you see that a helium is a product, then you know it's alpha decay. So that's really the one. I'm like, we're walking through how it happens and what the products are, but really I just want you to be able to identify it. Californium, that's what CF is. And in fact, californium was first discovered and described in Berkeley, California. So it's the University of California at Berkeley. It's near San Francisco. It's an area where they do a lot of chemical nuclear research. So what happens to the mass of californium if it undergoes alpha decay? It goes from 257 to 253, right? So that number drops by 4. What happens to its atomic number? It goes from 98 to 96. Then you got to find on 96 on your periodic table. CM, which is curium, which is named after Marie Curie. Okay, so she was a chemist that studied radioactivity and radioactive decay. She described a couple of radioactive elements. She worked with Becquerel. Okay, so that's the first kind of decay. You get a helium nucleus shot out. Beta decay is the second one, and the letter beta kind of looks like a funny bee. I always say that it looks like a bee with a foot. Remember how micro had a little foot on it? This kind of looks like a bee with a foot because the little piece comes down. So, and then sometimes they say it kind of looks like an italics bee. So that would be the symbol for beta decay. What happens in beta decay is a neutron breaks down into a proton and an electron. And the electron comes shooting out of the nucleus. And it becomes part of the area outside the nucleus. So our neutron becomes a proton and an electron. The proton stays in the nucleus. So you don't actually have it coming out. So that means that this electron is a product, because it comes out of the nucleus. But electrons don't change the mass, right? Electrons have no mass. So for this carbon-14 atom, what would the product be? What would the mass be if an electron comes out? It's still the same, so it's still going to be 14. There's no change in the mass. So a neutron becomes a proton. Neutrons have a mass of 1, protons have a mass of 1. So there's no change in the mass. But if a neutron becomes a proton, the atomic number, does it increase or decrease? We make a proton, which means that the atomic number increases. So the atomic number in this will go from 6 to 7. So the because a neutron becomes a proton. A neutron has no effect on atomic number, but a proton does. So atomic number increases by 1. So instead of being a 6, now it's a 7. So it's not carbon anymore. What is it now? Nitrogen. And in fact, look at the atomic mass of nitrogen on the periodic table. It's 14. So see how that's pretty stable? Okay, so this nitrogen 14 has 7 protons, 7 electrons, 7 neutrons, more stable than carbon 14. So by converting that neutron to a proton, it creates a more stable atom. And that's really why they undergo decay, to decrease in size or to form a more equal number of protons and neutrons. So let's try this last one. So Cu is what? What is copper? Good. So this is copper. So copper 66, when it undergoes beta decay, what happens to the mass? Stays the same, so it's still 66. I'm going to write over here that the symbol changes. What happens to the atomic number, though? Goes to 30. It's going to go up. It'll go up 1. Okay? And then, what is this new symbol? Zinc. And if you look at the atomic mass of zinc, it is 65.4, which is close to 66. So it's going to get a more even number of protons and neutrons, and so that makes it more stable. But I will tell you, this is the way to pick it out. If you see an electron as a product, it's beta decay. Okay, so that helium as a product is alpha. This electron is beta. So just look for that as a product. Everybody good? So then the last one. The last one is called gamma decay. Gamma decay doesn't actually make any particles. Gamma decay is the energy that is released during radioactive decay. So I think of this as being what happens when protons and neutrons shift their position in the nucleus. So when you've got a big atom like uranium with 146 neutrons and 92 protons, they're all crammed in there. And so they're doing this shifting to try and like position themselves, and that shifting releases energy. So in this, there's no particles released, there's no change in mass, there's no change in atomic number, no change in the symbol. So it's going to be what you start with is exactly the same, but they add this. So this, that symbol is a gamma symbol. And I'll tell you, it kind of looks like that. It's just I'm not good at drawing it. It almost looks like a skinny 8. Some people say it looks sort of like a weird Y. Okay, can you see it right there? It's a gamma symbol. It's the Greek symbol for gamma. Yeah, it almost looks like alpha turned sideways. Yep. So you can think of it, it's kind of like that. Sort of funny looking Y. But the way you can tell is you'll see the symbol, and I will use that symbol. I won't try to draw it on your exam. So this is what it'll look like. It'll look kind of normal. It won't look like an A or a B. Okay? It'll look like a funny Y, but there'll be zeros in front of it because that's saying no change in mass, no change in number. So that means that my atomic mass stays exactly the same. Atomic number stays exactly the same. Symbol stays exactly the same. So the thing that is interesting about gamma, though, is because there's no actual particles associated with this decay, this actually is the highest energy released of all of the radioactive decay types. The smaller the particle, the higher the energy. And so this, because there's no particle released, this has the highest of all. In fact, gamma really mimics what an X-ray is. And that's like an applicable thing because you've handled patients that have had X-rays, you've handled like taking them to and from. Sometimes you have to be in the room with them depending on the age. If you're talking about animals, you may have to stay in the room with them in order to have an X-ray done. So this is kind of the closest in terms of amount of energy, the closest to what an X-ray is. So you tell me, what's this first one? This first one is what kind of decay? Right. And even if you don't know the product, and I won't ask you to complete the reaction, but I would write, what would this one be up here? 222 would become 218. 88 would become 86. And 86 is RN, radon. But if I showed you this, you need to be able to tell me that's alpha decay. Okay? So I'd give you the entire reaction, and the way to pick it up is that helium. When you see helium, the helium nucleus is a product, then you know it's alpha. What about this one? What would the mass be for this one? Same. What happens to the atomic number? 20. And if it's 20, it becomes what? Calcium. But if you see this, then you're going to tell me this is beta. So that has an electron as a product. And then this last one. So there's the little symbol. So there's iodine 125. What would the product be? 125, 53, and I. Exactly the same. But if I showed you this, because I won't ask you to finish the reaction, but if I showed you this reaction, you should be able to tell me this is gamma. Okay? Alpha, beta, and gamma. Oh, that little asterisk, that means like higher energy, and then the I at the end would be lower energy. So sometimes you'll see that little star is just meaning that form of iodine has more energy than the product side. Okay? But that's pretty much what it's like. You'll see that in your e-text if you're reading it along, but that's really what that little asterisk is meaning. So here's an X-ray. So X-rays are not actually from radioactive substances. So you do not have like a lump of uranium in an X-ray machine. Okay? Just so as you know. Okay? Because then people will be like, I don't know if I want to go in here. You don't. Instead, X-rays are energy that's generated by a machine. So when you go in to use an X-ray machine, they like power it on. And so what it does is there is a power supply that can generate a beam of electrons. So it's basically like an electricity, but it can flow through a space. When it hits a metal, and usually the metal they use is tungsten. So you have this like sheet of tungsten that's right here. And you have a power supply that shoots electrons at this tungsten. Electrons energize the tungsten. So the metal gets energized. And then when it releases that energy, the energy that it releases is an X-ray. Okay? So that energy released gets focused on some part of you if you're having an X-ray. So what they know is this energy is strong enough to pass through soft tissues. So what is soft tissues? What part of your body is soft tissues? Flesh, like, okay, skin. What else? What's under there? Muscle. What else is under there? What's right underneath your skin? Some of us have more than others. Chub. Yep. So adipose tissue. So when they say soft tissues, think of stuff that's like soft and squishy. Okay. So blood, brain would be considered soft tissue. All the muscles are soft tissue. Your connective tissues, all of the ligaments and tendons, those are all soft tissues. So X-rays, that energy is strong enough to pass through it. But it can't pass through hard tissues. Hard tissues include bone and your teeth. So, like if you're a dental hygienist, one of the things that you do is you do dental X-rays. And so I'm sure you've all had a dental X-ray. So you come in and the dental hygienist is like, okay, open your mouth. And they like stick a piece of film in your mouth. Or they actually, it's all digital. So they actually stick like a little detector film. It's reusable then. They put that in your mouth. So that's on the other side of your tooth. So the film is here and your tooth is here. And then they stick this thing. They're like, okay, sit still. That little thing that's like up close to your cheek. And then what does the dental hygienist do? She goes out. She doesn't stand right next to you unless you're a little kid, and sometimes they have to. But generally, if you're like a functional adult, she leaves the room. And what do you hear? You hear like a little beep. You hear, and then she comes back in. Okay? That sound, that's as long as the electrons hit that tungsten metal. That's all the time. That little, that's it. That's all it requires to generate the X-ray. The X-ray then passes through. So I'm just going to do one tooth. So there's a molar, right? Because molars, they got those roots, those anchors, and it's in the gum. So we'll just pretend you only have one tooth because that's a little easier. That's a terrible looking molar. So it comes up. It's got like these little cusps. Yeah, that's a little bit, okay? That's a little deep rooted, but whatever. So in this, when they look at the film, the tooth looks what color? White. So the tooth looks white. The gum underneath, what color does that look? Kind of dark, right? It's kind of dark, more darker gray in color because this is soft tissues. But tooth is like bone. So your tooth is that hard tissue. There might be a root. The root is hollow. And so you might actually see kind of a gray outline of that root up through the very center of the tooth. But the top of the tooth looks white because it's really hard. The X-ray can't pass through it unless what is in that tooth? A cavity. And a cavity is a hole. So if you have a hole, or a cavity that is forming in that enamel in the surface of the tooth, it will show up as a darker spot. So that's what they look for. They're just looking to see if there's any kind of grayish, if it's not solid white up over the top, then they're looking to see, because like when you think of a cavity just means it's a hole. And so that's this little pocket that is formed. Now, you fell, your arm's killing you, it's all swollen, you go to the emergency room and they're like, oh, we got to get an X-ray, okay? Works the same way. So they have you lay your hand down, there's a film behind it. They have the X-ray machine is above. And again, super short period of time, X-rays pass through all the soft tissue. They cannot pass through bone. So when they develop the film, you can see the outline of the bone. But if there's a break, what will be in that break? You'll see like this dark line. And that shows that that's an area where the bone has cracked. And now there's blood in that space and that's soft tissue. So X-rays can pass through any cracks, but can't pass through any solid, rigid bone. So that allows them to look for fractures. Now, trying to look at like brain injuries, that's kind of hard because an X-ray is going to get blocked by a skull. So you could see a skull fracture, but you really can't see damage to soft tissues as well. But it works wonderful on hard tissues. Okay, so why do we care? Like why, other than like talking about, okay, protons, neutrons, electrons, yay, everybody knows how many there are in any given element on the periodic table. Why do we care about radiation? Well, because especially in your line of work, whether you're going into nursing or going into dental hygiene or even vet tech, in your line of work, you are going to be exposed to this energy. You may have to be with the patient while they're having an X-ray, or they may be undergoing radiation treatment for cancer, or they may actually have some radioactive source implanted in their body as a treatment. So understanding this is very helpful. So what's the issue with radiation? Whether we're talking about alpha, beta, gamma energy, or even X-rays, all of those produce radiation that they say is ionizing. Ionizing radiation can cause damage to molecules that it comes in contact with. This can make a molecule not work anymore. This could affect cell function. This could cause cells to die. This could cause cells to begin growing abnormally. So one of the things with cells is there's this control over how often they divide. And ionizing radiation can cause damage to that cell cycle control. So if a cell begins to grow out of control, that can lead to what? Cancer. So cancer is just when you have a cell that grows faster than it should and it creates a mass. And in some cases, those cells then begin to spread to other parts of the body. So we can be looking at things like cancer. We can be looking at diseases. We can look at things, it could cause cell death. And that can affect overall functioning of the body. So you want to understand the whole idea of shielding. To shield yourself from potential ionizing radiation, it really depends on the type of energy we're talking about. So the amount of energy that is released by these different types of radioactive decay is different. And the rule of thumb is big particles don't go very far. Okay, so alpha decay, remember we said alpha decay is 2 protons and 2 neutrons. That's a pretty big molecule. Alpha decay does not go very far. Alpha decay usually just goes a few inches from its source. So if you had a sample which is releasing or undergoing alpha decay, you may need to have some shielding within 2 to 3 inches of where that sample is. So it's only going to go a couple inches in terms of distance. Beta is smaller. Beta is just an electron. So beta actually goes further. So beta can actually pass a few feet. So a few feet from the source. So if you had a sample that was releasing beta radiation, it could go this far. So if it's across the room, not as much of a concern. Alpha, not as much of a concern unless you're holding on to it, like real close, okay? Gamma and X-rays, though, they can actually pass yards. Depending on the amount and the energy, you can be talking about like a basketball court kind of thing. So you're talking about a much longer distance. So if there is a sample undergoing gamma decay in this room, everybody's exposed, okay, if there's no shielding. Alpha, you'd have to be up real close to it. Beta, you would have to be kind of like pretty close, sitting within a yard of it for it to be an issue. So they talk about shielding. So what do I do? How do I protect myself from something that's an alpha energy releaser? Alpha can be blocked by a piece of paper, okay? So a lot of times with this, they'll use just either a piece of paper or a thin sheet of aluminum so you can block. So you can take a piece of foil and cover it. Wrap it up in foil, and that's enough so that it's not coming out, it's completely contained. Beta, because it has a little higher penetration, beta needs something thicker. So beta, they usually block this with plexiglass. And plexiglass, I always think of like at the hockey rink. So you know the shields that they put up around the hockey rink? It's plastic, but it's like half an inch thick. So I'm not talking about like a real thin layer. It's usually a good half an inch of plexiglass. It's a common way to be able to block beta. So that even if it was next to you, if it was in a little plexiglass box, you don't have to worry about it affecting you. Gamma and X-rays, you need to either use lead or you need to use concrete. So an X-ray, like in the hospital, at the doctor's office, or even at the dental hygienist's office, that is going to have the barrier that they put in is going to have either a 1/4 inch of lead or it'll have a foot of concrete. It'll have like when they build like a hospital and they're going to put in an X-ray room, they will actually have cinder blocks that bound that room specifically so that you decrease anyone outside of that room is decreased in terms of exposure. And you're like, it's really short. You know, that real short little buzz, it's not a lot, but if you were exposed to thousands of that, you know, all day long, taking X-rays all day long, that could build up and you could be exposed to enough ionizing radiation, it could cause damage. So for gamma, they're going to block this with lead or concrete. Because if you don't have a block, gamma rays pass all the way through you. And as they pass through, they can cause ionizing radiation, ionizing damage to tissues as they pass through. So if you have to give an X-ray and you have to be in the room, what do you wear? So you end up with the block. So here, alpha, we can block alpha just by wearing like a lab coat. Okay, gloves if you're handling it. All those things are perfectly fine to block because remember, paper, a piece of aluminum foil is plenty. Beta, though, we're going to use plexiglass. If they use aluminum foil, that's that heavy duty. You know that real thick aluminum foil that you can get that's like 3 times thicker than normal? If they use aluminum foil with beta, it's going to be that really heavy duty aluminum foil. Gamma, on the other hand, you wear the lead apron. Like if you go in to get an X-ray, one thing they always ask you is there any possibility that you're pregnant? And you're like, no. Okay, but irregardless, whether you're male or female, pregnant or not, they always put in a lead apron over your waist. Why? So whether you're male or female, what cells are there? Reproductive cells, egg and sperm, right? Because those cells will be used to create offspring, and you do not want ionizing radiation to cause damage to those cells. Because if you have damage to those cells, that increases the risk that your offspring will have those damages. So that's why whenever you get an X-ray, they always put a lead shield around your pelvis, and then the X-ray attendant, whether it's an X-ray tech or if it's the dental hygienist, that if they have to be in the room, then they end up putting a lead apron on. And now the new aprons, actually, they either put a lead collar on or the apron actually stands up. I don't know if you've seen those. So the new ones now for your X-ray techs, they have one that actually goes up over their shoulders, comes all the way down to their knees, and it actually stands up here, like the little collar. That's all lead. That's a lot of lead. It's pretty solid, pretty heavy. It's a good 30-pound lead apron that they wear if they have to stay in the room with you. The reason they have this up here is because of this gland. Do you remember this? The thyroid. Because they have found people that are X-ray techs that are doing nuclear medicine, that are in rooms where they're handling and around radiation and X-rays and specific like radiation beams a lot, that they have found that they develop thyroid issues. And so this lead collar helps to protect you from that. Okay, so if you're handling, you're like in the room where X-rays are being used, and they're going to use a lead apron. Other things, a film badge is important. And if you work where you're using X-ray equipment, doing X-rays all the time as a dental hygienist, you should have a film badge. A film badge just clips to your shirt, and every month they ship the film badge off because they develop that film badge and it indicates how much energy you have been exposed to in that 30-day span. And if you're over the amount of exposure, then you need to be moved so that you're not in that same place for a period of time. So there's like a maximum exposure, maximum healthy exposure that the, it's not the CDC, but it's sort of like the Health and Human Services that they have developed to say, you can safely be exposed to this, but above this, it puts you at risk. So you would need to not be the one that's working in the X-ray room or working with the patients that are undergoing radiation treatment. So a film badge is really important. So they talk about, well, how much is too much? Okay, so looking at this, this is from the 1940s. Okay, so in the 1940s, when X-ray machines were first developed, this was something that was for real they started to do. Where's my Zoom? Well, nope. Well, and it won't let me zoom it anymore. But can you see the little kid in the left is standing up and standing on this little box? That box was an X-ray machine. So in the 1940s, you would go to the shoe store and they're like, oh, let's take an X-ray of your foot so that we can be sure your shoe fits right. When X-rays first came out, they were doing X-rays like mad on people at all the fairs. They were like, get an X-ray of your arm. Okay? And the amount of energy you had to be exposed to back then was 1,000 times more than what it is now. Our film is super sensitive. Digital film requires very, very little exposure. So that means like, you know, that you hear, this was like kind of sound. You're like, so it really came in. They actually had X-ray machines in shoe stores. That was sort of like the rage. Yes. And then the whole health and safety people came out and went, you know, this is not a good plan. So this kind of phased out. It was only about the 40s to the 50s. And then you saw these like disappearing because they were really heavy because they were lead lined. And so they would take the lead out so that they could move the box around, because having the lead, which blocked any of that energy, having the lead was actually a pain in the neck because you couldn't move the X-ray box around. Yeah, not so great. Okay. So just know that back when they first started discovering these kinds of things and using them, it has come a long way in terms of technology and safety precautions. Because radiation sickness, exposure to large amounts of radiation, can cause cell death, especially cells that are growing rapidly. Cells that are growing quickly are the most susceptible to damage by this ionizing radiation. Well, what are cancer cells? They're defined as cells that grow faster than they should, right? Rapidly growing cells are a characteristic of cancer cells. So this is why using radiation as a way of treating cancer,
It slows it down.
it's not just slows it down, but that ionizing radiation can actually damage those cells and kill them. Okay? So that's why the goal of radiation therapy for cancer, the goal is to destroy these rapidly growing cancer cells. The problem is it also destroys other rapidly growing cells. So what cells in your body grow quickly? They grow and replace themselves quickly, like every 3 to 5 days. So blood cells are in constant production in your bone marrow. They do take about 2 months, but they're always like starting production. So your red blood cells in your bone marrow constantly growing. So side effects. If people undergo radiation, then that means that their red blood cell production is inhibited. So oftentimes they become what?
Weak.
If we decrease red blood cell production, they're going to become weak, and that could, but no red blood cells makes you, what do you call it? What's the term? Anemia. So anemia results. Anemia by definition is just low numbers of red blood cells, low oxygen carrying in the blood. It'll also decrease your white blood cells because those also are formed in your bone marrow. So that's going to make you what? If you don't have a lot of white blood cells, what do you call that? You're susceptible, right? So you're at high risk. They call this immunocompromised, right? So remember with COVID, this was the group, I think I spelled it right. This was the group they're most concerned about because this was the group that when they would get COVID, they would have these flu-like symptoms that would develop into pneumonia. They would have fluid in the lungs. They were the ones that ended up in ICU, ended up on ventilators. So being immunocompromised is because if they don't have a lot of white blood cells, then they're not going to respond to infection quickly. So they're going to get, an infection is going to get much worse. So they were the ones that were really cautioned, like you really want to isolate yourself. You really want to try not to go out into large groups. And if you are, you definitely need to wear a mask because you really want to try and decrease your exposure. Okay? Can you think of other cells that are growing quickly? What other cells grow quickly? That you end up with these side effects of radiation treatment. What kinds of problems do people that undergo radiation have? They lose their what? Hair. So hair. The hair follicle, the hair root, is an area of rapidly growing cells. These cells expanded almost a half an inch a month. Okay, so the hair root decreases, it dies off, and so what happens to their hair? They have hair loss. Okay, what about their skin? Patients that undergo radiation, what's common?
They look dry.
Okay, their skin gets really dry. Oftentimes they get really rashy looking. They get rash, they get like rashes, the skin breaks down, especially if it's in the area where they're being exposed to an external radiation beam. So they'll get rashes, dryness. What about their GI tract? What do they have? What's another side effect of radiation treatment? Nausea, vomiting. This is because your entire lining, I knew that was going to happen. your entire lining of your GI tract from your mouth, your esophagus, your stomach, small intestine, large intestine is replaced. The lining is replaced every 3 to 5 days. Constantly. It's constantly growing. So you can see where, oh, I knew that would happen too. So you can see that that would lead to nausea, because like the acids that are secreted are going to irritate the lining because the lining is not growing and replacing itself as quickly. The small intestine lining, you don't have to, your absorption is not as good. A lot of times you end up with diarrhea because food doesn't get digested. It just kind of like passes through quickly. So you can have all of these GI tract effects. I will tell you, my mother went through radiation and chemotherapy for cancer when she was in her 40s. And she said like everything tasted like a penny. She was like, it tastes just like metal in her mouth. Her taste buds, your taste buds are replaced about every 3 days. She couldn't taste, everything just tasted black, just bland. So it had this negative effect. So she was like, I'm not even hungry because nothing tastes good. So GI tract, that should be an I. I can't write that low, sorry. GI tract. So those cells are affected. Go ahead, Candy.
What are those big knots that people get in their arms when they
Is that when undergoing radiation or is that from chemotherapy? Because that can be.
I thought it was from dialysis. You talking about right here?
Yeah.
So that can be like because of like from dialysis, like those where the ports were. But if they're undergoing radiation, usually radiation, if you're doing like, so say that they find like melanoma. So melanoma is like a bad mole, a mole that's gone cancerous. So if they find it very early, they might want to spot treat. So they will cut it out, so surgery to remove it. But then they might want to do radiation in that area. That area of the skin typically gets really red, rashy. It looks really irritated. And it's all because of this high energy. So it causes damage. The goal being we're going to destroy any rapidly growing cells, cancer cells, but it does cause cell damage to like skin cells. So in terms of like the knots and stuff, I would go more with like what can happen if you're having injections with chemotherapy drugs that can cause blood vessel damage. And you can end up with like knots that are formed much more so than with radiation. So nausea, you can end up with diarrhea. You can end up with actually poor like malabsorption. So that means like you don't absorb as much nutrients from the food that you're eating because you're not processing them. My mother's biggest complaint was everything tasted like a penny. She was like, it feels like I got a penny in my cheek because everything I put in my mouth has this weird metallic taste. And that was just the taste buds. Okay, so really the goal is we want to destroy rapidly growing cells, but you have these side effects that you're also going to be affecting the normal growth of other rapidly growing cells. So this is Marie Curie. So Marie Curie, I will tell you that she is the one, she actually isolated radium, which is number 88. She extracted it, and it was named radium because it glows in the dark. So she actually kept this little bottle of radium that she had extracted. It was a little vial of it. She kept it next to her bed, so it was like a nightlight. She died of cancer, okay? She died of lymphoma, and this was before they really understood what this ionizing energy could do. So she ended up developing cancer of the white blood cells, which is what lymphoma is. So that's like terrible to say, but that one says you're looking more radiant every day. That's terrible. But it was funny, but it's a terrible thing to say. But in fact, like that's what ended up, she like ended up with severe radiation poisoning because of that exposure that ended up leading to cancer. Okay, so thinking about dosage, you really have to have kind of high exposure before you're going to start seeing like major life-threatening effects because of high ionizing radiation. Most people are exposed to 5,000 to 20,000 normally in their lifetime. You're exposed to some of those gamma rays, they come from the sun. Okay, so there's like cosmic rays and other rays that actually carry this energy. So you are exposed. You can't really like put a lead shield over your head all the time. But for most people, it doesn't end up causing issues. But you do have these higher levels can cause mild and then more serious types of radiation poisoning. So here's the example. The example of radiation poisoning and effects happened in 1986. So I'm not sure how many of you were alive then, but I remember this because I was like in high school, and this happened in the Ukraine. So Chernobyl was this nuclear power plant that was in Russia. So it was in the Ukraine. So at that time, Russia and the Ukraine were all one. Then they split off later. So in the Ukraine, you had Chernobyl. So they didn't do all of the maintenance and the updating. Times were tight. The 80s were not. That was times of inflation. Countries really didn't have a lot of money. Unfortunately, they built a nuclear power plant and then they didn't really maintain it the way they should. So this is how a nuclear power plant normally works, is you have a radioactive source, and this is uranium. So uranium, the normal uranium with the 23892, it undergoes alpha decay. So in that alpha decay, it breaks down into thorium. It also releases gamma energy. Well, then that thorium actually undergoes beta decay twice, reforming a slightly smaller uranium that then starts this process all over. But every single time it undergoes decay, it releases energy. So that energy, you take this uranium and you put it in water. And that energy heats up the water. So it actually heats up the water enough so it makes the water boil. Well, water, when it boils, becomes steam, and that expands, and that runs like a steam generator. So this is how nuclear power plants work, is they use energy to heat water, make steam, and cause turbines of a steam plant to function. So the goal is we want to make sure that we take this uranium and it's put in these little shielded jackets, and we only open it enough to make as much energy as we want. And if you don't need the energy, like at night, or if the weather's cool, if their energy is like demand is low, then you like kind of put that uranium down in its little jacket, and it's not going to heat the water up so much. So with Chernobyl, what happened is they went through and they're like, we're going to test and see how this works. So what they did is they actually turned off the adjusters to be able to do their maintenance. So that meant that now the little uranium rods were out too long. The water got too hot and it didn't get circulated. So it began to boil without going off into the steam generators. So it got so hot that it actually blew the lid off of the pool where the water was. So the water converted to steam and literally blew the lid off of the top of that energy, off of the power plant. And people saw it. Like, people actually heard this huge explosion and saw it like miles away. So this energy, the amount of energy that came with this explosion was enough to actually cause what's called fission. Fission is when uranium literally splits into two different atoms. So it made cesium-137, which is radioactive, and iodine-131, which is also radioactive. And that got shot into the air with that steam. So all of that goes up into the atmosphere. Well, they actually started recording increases in radiation in France. So think about where Russia is. So in France, they're like, why are so they're constantly like monitoring radiation levels just globally. And they started seeing this happen. So they knew something had happened. So finally the Russians fessed up and said, well, we had a small problem, but we got it under control. And so that's when like there's now like a world nuclear regulatory commission. They're like, no. They like had to go in and they actually had to like dump concrete over this this reactor. So they like sealed it in, they think, or they say, but they actually moved. They had to evacuate about 350,000 people were evacuated from that entire area, and very few people still live there. just to show you what they found, before 1986, only about 1 person per million up in that area developed thyroid cancer, so cancer of the thyroid. But in 2003, it's up to 60. So that means like this caused 60-fold increase in thyroid cancer development because one of the things that shot into the air was iodine. And where does iodine go when you ingest it? Straight to your thyroid. So they did see that it definitely ended up having an overall effect, but this led to a lot more regulations on nuclear power plants, like globally. So a country can't be like, no, you can't come and check our stuff, because it's been agreed that if you're not going to maintain your nuclear power plants, then you don't need to have them. Okay, so there is like more multi-nation type of thing, more like NATO that goes around and checks that. So that's why. So the last thing, and we're not going to do half-life, which is the math part. So there's not going to be any math in this. Okay, but the thing to remember is looking at this use. When you want to use a radioactive substance, you can use a radioactive substance in a couple of ways. So you can use it what's known as diagnostically. So diagnostically, and I can show you it on this one. Diagnostically, see this. There's iodine 131 and iodine 123. So these are 2 radioisotopes of iodine. Both of them are used in diagnosis or treatment of thyroid disorders. So notice the half-life difference. So I'll just tell you, half-life is the amount of time it takes for half of that radioactive energy to disappear. So if I have this sample and it's releasing energy, half-life is how long does it take before half of that energy is gone, okay? So we're not going to do any math with it, but just think of that. If I've got 100 units, 1 half-life, I've only got 50. Okay, so it's how long does it take for half of it to disappear or break down. Iodine 123 only takes about 13.2 hours. Iodine 131 takes 8 days. So iodine 123 has a much shorter half-life. Shorter half-lives is what they like to use for diagnostic purposes. So if you have a patient, if we have a patient and they come in and they have an overactive thyroid, they will give them iodine 123. They give them a very small dose. They want to give them the smallest dose that they can detect. They inject it. All that iodine goes to the thyroid. Then they can monitor, where does the thyroid go? Where does the iodine go in the thyroid? Is it uniformly dispersed, or does it all go to one spot? Because if it all goes to one spot, that shows an irregular area. That's an area of abnormal cells. So that may actually show them that there is some hyperactive or cancerous cells, abnormal cells within that thyroid. So if they have an overactive thyroid, they're first going to use iodine 123 with the lowest dose possible. Then they can monitor, because it's releasing energy, they can monitor where that energy is, and they can actually like map the thyroid to see which side is more active, or is it uniform, because it'll like literally like show up as kind of like a glow on the sensor. If they find that there is an area, then they can go back and treat you with iodine 131. Iodine 131 has a much longer half-life. They give you a higher dose. It lasts longer, but that collects in the thyroid, and over a month, it will actually release energy and destroy the thyroid. So if, say you have thyroid cancer, or they have an overactive thyroid they can't control, then they can therapeutically, so diagnose, lowest amount, short half-life. Therapeutic, you're going to use a higher half-life length. So iodine 131, you give a higher dose. It's in the body longer, and it ends up concentrating in the thyroid, and ends up causing damage. Because so now you've treated the cancer though. So you've destroyed the thyroid and the abnormal cells too. During the time this patient is undergoing treatment, they should sleep by themselves. Why? Because they actually have radioactive iodine that is releasing this ionizing energy. If they're sweating, there's potential that they could actually be sweating some of this iodine. So they should sleep alone. They should use a toilet that no one else uses because in theory, urine and feces could contain this iodine. Wash their sheets separately. Wash their utensils, rinse that separately because even saliva, any secretions potentially could contain some of that iodine 131. After the thyroid is destroyed, then they just put you on thyroid medicine. So then they give you artificial thyroid medicine for the rest of your life. So, because sometimes that's the only way to balance it. That's the only way to keep the thyroid from causing issues. So here's like the picture. Here's a good picture right here. The top one, so remember your thyroid is like two glands connected by an isthmus, which means a bridge. So see how that looks kind of like two little lobes and a little bridge between? So that one at the top, that's normal. So it's kind of like uniform all the way across. Like the whole thing, the color, that one colors. The ones at the bottom I found online, those ones are really good. So here's like, this is one side, here's the other side. You don't even really see the bridge. That looks good. Okay, but look at with Graves' disease. See how dark that looks? That tells you that the iodine is like concentrated in that area. This one down here, see how one side is really big and dark and the other side's really light. So they look to see how much energy is being released throughout the thyroid. This one they would want to treat. What about this? Yeah, so this is like this big, huge, large with that really dark center. That dark spot shows high activity. You would want to treat and destroy this. Oftentimes, the only way to control Graves' disease is to do this treatment. So the diagnostic, here's the thing. Diagnostic isotopes, you want to give them the smallest dose possible, and you want the shortest half-life so that it clears from the body quickly. So if it's only 13 hours, if they give you a dose of 100 to do your scan, within 13 hours, half of that's gone. In another 13 hours, we're down to 25%, so half of the half. In another 12 hours, so in a couple of days, it's to nothing. But if you have to give them therapeutic dosage, you're going to give them a larger dose, and it's going to be one that has a longer half-life. And the patient may have to do those precautions like washing their bedding, sleeping separately, showering, using a separate toilet, all of those things to try and minimize exposure to other members of the house. Okay? There's another one. It's kind of neat. So like there's lots of different ways to be able to use radiation. The first one shows a ventilation scan. So this uses what's called xenon 131. It's a gas that releases radiation. So they go, okay, here's what I want you to do. I want you to inhale this gas and hold your breath. So you put the pipe in your mouth, you go, and all this xenon goes into the lungs. And so it releases energy and you can see where that gas goes. So if they have like a blockage, you'll see an area where it doesn't show up. And then when they exhale the entire thing. So it doesn't stay in the lungs. So it's a gas, you inhale, when you exhale, it comes back out. So that's pretty cool. The one over, and that one shows like normal. See how it looks just kind of like all gray? So that just shows like the xenon is distributed evenly. The one over on the right uses technetium-99. They inject this into the blood. This goes to the blood vessels surrounding the lungs, and it looks at blood flow to different parts of the lungs. So can you see those areas where it's light? They call them cold spots. Those areas show poor blood flow. So that could be an area of the lung that's scarred. So if you get scar tissue, you're not going to have good blood flow through that area because there's damage. And so those cold spots help them to determine if there's areas of the lungs that have been damaged. So they've used this one a lot. This has been another one that they used a lot in COVID, trying to determine just what kind of lung function patients are having post-COVID, after they've been on a ventilator and then they get off a ventilator, and how well are they how are they recovering? They can do these kinds of scans that doesn't leave a lot of you're not radioactive walking out of the place, but it helps them to diagnose without having to do a lot more invasive types of surgeries. Okay, so that's really the big part of chapter 2 I wanted to cover. So I'm going to quit there. Okay, this finishes information for chapter 2. Nothing on that we haven't talked about, so there's no half-life questions. Okay, so there's no half-life questions. There's ones like this. You don't have to worry about this because we didn't talk about it. So there won't be any half-life math questions. We didn't talk about it. There won't be any on it. Only stuff that we talk about is what you have to worry about and do in your study. Okay, so if you get stuck and you're I'm not 100% sure, you can go back and look. Remember, I post these PowerPoints as well. So these are posted in Moodle as the marked up PowerPoints. And so I'll make sure that anything that you don't have to worry about, I'll X that screen off so you can kind of check yourself. Okay. All right. Well, I hope you have a nice Labor Day. I'm really excited. I'm going to see my grandson. I haven't seen him. Nope. Monday night, no class. Monday night's Labor Day.